well as he's a professor in Tundon School of Engineering in New York. He did his PhD from Potsdam, and then he was postdoc at Marburg and Yale. He has very wide interest, and he's very well known for his work in turbulent convection, mixing of passive scalars, machine learning applications for turbulent flows, and he's heading this project on superstructures in Germany. So I will not speak more about Jörg. I think everybody in the audience knows him. So I invite Jörg to start his lecture.
Yeah, thank you very much, Mahendra, for this kind invitation. I'm happy to give this talk today, even though I would be much happier to be in Kanpur, sitting next to you and giving this talk. But anyhow, we have to make the best out of it, of the whole situation. Yes, so I'm going to talk about large-scale flows in turbulent convection, and I will say a few words about our simulations and our machine learning approach to this problem. The work is funded by the German Research Foundation, DFG, within a priority program, and by the Carl Zeiss Foundation within a project on deep learning in computing time, support by the German supercomputing centers. So my talk will be divided in 3 parts. In the first part, I'm going to present some very recent results on large-scale structures which form in extended convection layers. That's a joint work with Philip Fievig and Janet Scheel. Then we are turning into the machine learning topic, and we are talking of what is one way to obtain reduced models of turbulent convection, and the algorithms we have specifically in mind are so-called reservoir computing models. That is a joint work which is going on already for a while with Sandeep Pandey, with Florian Haider, Erik Fonda, Ambrish Pandey, and Srini. And at the very end, if there's some time left, I will tell you a little bit about our very recent efforts to extend this machine learning algorithms into the quantum computing world. That's an ongoing work with Florian Haider and Philipp Pfeffer. So that's really brand new stuff. But let's start first with the classical things. And let me motivate my presentation with the example of solar convection. We know that solar convection processes which take place in the outer shell of the sun are organized in a hierarchy of structures. We have the granules, which have a typical scale of 1,000 kilometers. They live for 10 minutes, and there's a characteristic velocity of 3 kilometers per second on the so-called smallest level. That's a very regular pattern, and here you see a picture of solar granulation at the surface of the sun. The next step in this hierarchy, or the next prominent feature in this hierarchy, are the so-called supergranules, which are about 30 times larger than the granules. They live for a day, and they have a weaker directly be detected. So, and this is either by granule tracking or by helioseismology. And the point is that they are still not fully consistently reproducible in simulations out of the granules. So there is still some gap in understanding these structure formation processes. For completeness, I would also mention the structures at the largest level, which are, however, highly debated. That's why I put a question mark behind the giant cells. These would be convective structures which stretch out over the full convection zone. They are very long living and typical velocity which can be assigned with them is very, very small compared to the others. And it's really still an open issue in the solar research if these structures exist at all. So our motivation is to take the simplest possible model of turbulent convection and to see if we can learn within this simple model something about the structure formation, which could also be interesting in view to applications as solar convection. It is clear that in terms of the parameters, we will be by orders of magnitude away from reality, but nevertheless, it's more about understanding the basic mechanisms which are behind these structure formation processes. We take the Boussinesq model, as you can see it here, with the equations which are given in the top of the slide, and we take a really extended domain with an aspect ratio of 60. For simplicity, we choose a Prandtl number of 1, which is about 6 orders of magnitude above the one which would exist in the sun. And we take Rayleigh numbers, which are small, as you can imagine. And here are the two definitions given, which are specific to the set of temperature boundary conditions that we are taking. So the following set of boundary conditions are taken at the top and at the bottom of this layer. It's the no-slip boundary condition or the free-slip boundary condition for the velocity field at the top or bottom and bottom. And in terms of the temperature field, we either prescribe the temperatures at the top and at the bottom, or we prescribe a constant flux at both planes. The sidewalls are always periodic. That means we have, in principle, 4 different arrangements which can be compared with each other due to these 4 different boundary conditions. If one wants to compare and relate these studies, one has to be a little bit careful in the sense that the Rayleigh numbers for the Neumann and the Dirichlet case are connected to each other via the Nusselt number. This is, for instance, explained in this physical review letter by Charlie Döring and Hans Johnston. The Nusselt number definitions are given here. So we are basically determining the flux at the top and at the bottom walls. And in the Neumann case, the Nusselt number is given by this relation. The Reynolds number is the same definition in all cases, as you can see it here at the bottom. So then we are running these numerical simulations, and this is what you would get. So what you see here are 12 panels. We have 3 different Rayleigh numbers, 10 to 4, 10 to 5, 10 to 6 in each row. And we plot the temperature field close to the surface, close to the bottom wall. As you can see, we are somewhere inside the thermal boundary layer. All are snapshots across the whole cross section. And you recognize that the structures are very different when you compare the typical Dirichlet case with prescribed temperatures and the Neumann case with prescribed flux. In the right columns, we observe the typical structures which we term turbulent superstructures. These are the patterns which remain to exist in the fully turbulent case. And you see that basically qualitatively the same structures appear for the free slip and the no slip case. So that means the velocity boundary conditions in both sets of simulations seem not to matter. Now we go to the Neumann case, and what we see there is basically one big pair of convection cells. And so you have a big red spot, and you have a big blue spot. which is distributed across the corners. In some cases, that's because we are using here periodic boundary conditions in the horizontal directions. But you have this very big feature. And on top of it, you have the modulation with very fine granules. So that's exactly why we term this structure a supergranule, also to distinguish it from the standard superstructures which we have studied in the past years. So the message is temperature boundary conditions do matter. Let us take a look what we can learn when we go back to the onset of convection. And we have to go back into the 60s of the past century to Hurl et al. Or to Sparrow et al., which have studied the linear stability of an infinitely extended convection layer with plates, which is enclosed by plates of finite conductivity. So kappa fluid is the fluid conductivity, kappa solid is the conductivity inside the plates. And we have basically two limits. The one limit is that Kf by Ks is equal to 0, which basically means that we have a perfectly conducting plate. So the temperature which you want to obtain is immediately set up. For instance, after a plume is detaching from the wall. That is the typical case which we call the Dirichlet case. And as you can see, we get the very famous critical Rayleigh number of 3.11, and we get our 1708 as the critical Rayleigh number. So 1708, 1708, I should formulate this correctly. The opposite case is when this ratio turns to infinity, we have basically a perfectly insulating plate. And then we are at the Neumann case. The critical wave number is 0. And the critical Rayleigh number is 720 when we have no slip boundary conditions for the velocity field. It is 120 when we have free slip boundary conditions. Okay. So there is we know from the linear stability theory, there is a tendency of the structures to stretch out in the whole layer. That is meant when we talk about a critical wave number of 0. And indeed, what we observe is when we start our simulations from the equilibrium, from the diffusive equilibrium state, and we perturb the temperature equilibrium a little bit. The fluid is at rest. That is the initial condition for all our simulations. And then we watch the evolution. And you see it again for the temperature in the top panel. So it develops bigger and bigger structures. It's a little bit like what you would observe in binary mixtures. So you're getting coarser and coarser patches until the final cell here is formed. And that takes extremely long, as you can see. And that's probably one reason why nobody has seen it so far, because you have to run, in this particular case, 10,000 free fall time units, which is a very long period. The process can be also seen when you're taking the Fourier transform of the temperature field in the corresponding plane. And it does not matter too much which plane you are taking, you are observing always the same feature. Namely, that the Fourier spectrum gets concentrated in the 4 wave vectors around the homogeneous mode. And these 4 wave vectors are, for a given resolution and for a given aspect ratio, the 4 smallest wave numbers, or the 4 smallest wave vectors, horizontal wave vectors, which you can access in this simulation. So that means the structure grows as long as it can. And it stops growing when it reaches the full size of the area. When you're averaging this with respect to the angle, you see it here for the spectra, and you see it for all quantities, co-spectra, temperature, and vertical velocity. And you see it for all Rayleigh numbers. So we see it in the weakly turbulent regime, but we see it also in the fully developed turbulent regime. The structure does not go, and it's just that the higher the Rayleigh number, the longer it takes to form the structure. So you see here it takes 20,000 free fall time units. So it gets longer and longer, but this is always the final state which we obtain. Wait, there's, yes. There is also, we can also analyze which share of the global heat transfer takes the structure. And we have decomposed basically in Fourier space the temperature field and the velocity field into the big cell structure and the rest. And you see that the big cell structure contributes increasingly more with time to the overall heat transfer. The Nusselt number itself, the global measure of heat transfer across the layer, remains constant. So we are trying now to understand this behavior. And again, we take a look back into the literature and we go into the year 1980 and a paper of Chapman and Proctor, who actually continued the work which has been done by Hurl and Sparrow in the 60s and asked themselves what happens right above the onset when we take a finite box. And here is the critical stability curve, which you see here. It's Rayleigh over wave number, and we have the 720, which I mentioned, at a wave number of 0, and then we have this quadratic dependence when you move away from that point. So they basically do an expansion, as you can see it here, and they converted this whole machinery into a finite domain. So we have a box or a 2D layer of length L, and then we basically do a perturbative expansion of the Boussinesq equations. We are looking for fixed points of this new system and we study their stability. And when you do this work, you see that the stability at a certain scale L always gives rise to a new linear instability out of these structures on a somewhat larger scale. So it's like a process of instabilities on growing and growing scales. So that means you have first smaller structures, they become unstable, give rise to structures at a larger scale, and then it goes on and on and on and on. That is what they determined for the weakly nonlinear regime right above the onset of convection, when you basically can formulate everything in amplitude equations. So let us summarize a little bit what we have so far. We have seen that constant flux boundary conditions lead to the formation of a supergranule in an extended domain at Prandtl 1. It's independent of the velocity boundary conditions. It's observed for all accessible Rayleigh numbers. The larger Rayleigh, the longer it takes to form the structure. We know at the onset in an infinitely extended layer, the critical wave number is 0. We see that for a finite domain, the system with the same thermal boundary conditions develops convection cells which grow as long as they can, and they can as long as the wavelength is below the side lengths. So we can conclude that the convection does not forget where it comes from, even though it's fully turbulent. So it remembers its primary instability mechanism. Can we quantify this in the turbulent case? And we tried. And what we did is the so-called Lyapunov analysis of our fully turbulent convection flow. What is a Lyapunov analysis? Well, we can think of our Boussinesq equations as a dynamical system, as it is written here, a nonlinear dynamical system. And the Lyapunov exponents and the corresponding vectors, eigenvectors, measure how quickly with respect to time two trajectories separate off each other in the high dimensional phase space. It's a measure of the chaoticity in the system. And I have tried to sketch this here. So the evolution of our turbulent convection flow is a trajectory in an extremely high dimensional phase space. And we are basically taking a system that has nearly the same initial conditions, and we watch how far it moves away from that trajectory. That's the picture behind the Lyapunov analysis. So the problem is we have a tremendous number of degrees of freedom. We are not talking about a Lorentz attractor in 3D. We are talking about a flow in a 1.5 times 10 to 10 dimensional space. Yeah, that makes it immediately clear that we cannot get the full Lyapunov spectrum, which would mean that we have to solve 1.5 times 10 to 10 linearized Boussinesq equations together with the original nonlinear Boussinesq equation. We cannot do this. But what we can obtain is the primary Lyapunov exponent and the corresponding Lyapunov vector. And that's what we did. And in the following, I mostly visualize the temperature component of this Lyapunov vector to get you an idea about the structures. So here once more, the linearized system. And I would like to mention that this is not new. We have not developed this. This has been applied in the weakly nonlinear regime some 20 years ago, as you can see here by these references, in order to study pattern formation and defect dynamics, as you can see here. So we have verified that our code does the same, what has been reported in these works 20 years ago or 15 years ago. Here's what we get for our simulation. This is the no slip case in the top and the free slip case at the bottom. In the first row, you always see the temperature field, full cross section, and then we have a zoom into a smaller area, which you see in the subsequent panels. And below that, there's the corresponding temperature component of the Lyapunov vector. And the structures look very similar as the temperature fields themselves. But you see the high amplitude regions here in these rich structures, which typically correspond to strong up and down flows. So these are the regions which are most susceptible to instabilities. These and the scale of these structures is basically what tells you what is the present scale of instabilities in the flow. So where to analyze the Lyapunov vector? We have looked at these components, and you can do it basically in each plane, but we decided to take the ones where this component is largest, and there's a clear local maximum in the Dirichlet case. In the Neumann case, we go as close as possible to the walls, not going directly at the wall, but into the thermal boundary layer. And then we get the following. We see by means of the leading Lyapunov exponent and the spectrum which we obtain from the leading Lyapunov vector that this quantity has the same tendency, the same behavior as the structures themselves, namely that there's an instability scale which gradually grows, and it grows until it cannot grow anymore. And 60 is exactly the limit. More is not possible for a wavelength in our system. So the Lyapunov analysis confirms that basically there's a local instability. And in this case of boundary conditions, it gives rise to larger structures, further and further larger structures, until the box size is reached. So we have basically quantitatively shown that this is indeed the case. You see in the Dirichlet case, that's not the case. This wavelength lambda, which we assign with the Lyapunov vector, remains constant and it remains well below 60. Yeah. What's next? Currently, we are asking ourselves, well, how can we stop?
One question?
Yes?
Yeah. So in the earlier case, for the Neumann condition,
yes,
the saturation is not a nonlinear saturation. It's some kind of limiting situation. So is there nonlinear saturation for the exponent, I mean, instability? How does it saturate the instability, if at all?
Which instability do you mean?
So the mode is growing, no, all the time. So growing to bigger and bigger. But you said that it saturates when it reaches the box size. But in modes or secondary modes like Lorentz equation,
all quantities go into a statistically stationary regime once the box size is reached, and then we have steady state turbulence. Many quantities are already statistically stationary before, but as you can imagine, as long as we have this growing structure in our flow, for instance, things like fluctuations, etc., still have trends with time. Yeah, okay. But we have run that longer, and we don't see any change anymore. Once the box size is reached, the flow is in statistically stationary turbulence.
Okay. Okay, we'll discuss in the question answer.
It's a nonlinear saturation, certainly. I mean, we are highly nonlinear. We are fully turbulent. So it has to saturate nonlinear. It cannot blow up exponentially forever. That's impossible.
Sure. Okay.
Yeah.
Please continue.
And now it's Mahendra, now it's exactly the point. The question is now, what stops this instability? And what to do next is to switch on rotation about the vertical axis. And that's exactly what we have done here. So this is a series of simulations, and you know, the smaller the Rossby number rho, the larger or the stronger is the rotation. And you see for very large Rossby numbers, basically no impact on the structures. And then you decrease Rossby and you see how this big cell is basically decaying into smaller structures, which then stop to grow. Yeah. So rotation of the whole plane about the vertical axis limits the growth. Another extension is a joint work together with Ambrish, Pandey, and Srini. It's we introduced in these models temperature-dependent diffusivity. And then we are able to break the Boussinesq behavior, and we can basically mimic a flow that is effectively low Prandtl at the bottom and high Prandtl at the top. That's something which I'm not going to detail here. I just want to refer to this. Okay. Let me summarize part one. Supergranular aggregation in an extended Rayleigh-Bénard convection flow with constant flux boundary conditions is observed, and this is independent of the velocity boundary conditions. And we have shown by a Lyapunov vector analysis that the trend to develop instabilities at increasingly larger scales continues until the box size is reached, and it also continues into the fully turbulent regime. The system does not forget where it comes from. Yeah. Okay, and more details on this part can be found in a paper which is open access, and feel happy to take a look. So now we are coming to part two. We have all these simulation data, and we generate more and more data, and this asks for new ways to reduce the data and to extract the information. And one way is machine learning, as you all know. And I have borrowed this picture here from this very nice review article by Brunton, Nowak, and Koumoutsakos. There are basically three groups of machine learning algorithms, which are supervised and unsupervised, and in between a mixture of both, which is semi-supervised. And when you see and look into these mathematical tools which are here applied, then you see that many things are known already for decades. They have never been termed machine learning as today, but POD is, for instance, something which we know already very well. K-means clustering, spectral clustering as well. But anyhow, these days, it's all machine learning. The analysis I'm going to present now in the following are two supervised machine learning algorithms. We are going to apply machine learning in turbulent convection, and we will reduce the complex temperature patterns to a transport network. This is a classification task which we are doing by means of a deep convolutional neural network. And the second part is machine learning of turbulent convection, where we aim at describing the low order statistics within a machine learning model that does not solve the Boussinesq equations. And we are using for this second part a recurrent neural network, in particular a so-called reservoir computing model. Let's start with the first part, and let me explain very briefly what we had in mind. Well, these are the data, and now we would like to classify the information in these data. And typically, because we have in turbulence 3D or 2D data, which are already quite big and quite comprehensive, one has to do a data reduction step in between, which in this case, for instance, is an averaging that brings us to these patterns, large-scale patterns in our turbulent convection flow, which we obtain from these data records. And then the idea is to develop machine learning algorithms that can reduce this information even further, namely to basically classify all the regions where we have a strong convective heat flux. And that can be that cold fluid falls down or hot fluid moves up. And this is illustrated in these three pictures at the bottom, where we plot vertical velocity, temperature, and the product of both in the midplane. And you see this pattern of these ridges, which we see here, are exactly the local regions where we have an enhanced convective heat flux. So this is like a temporally evolving network, which we want to identify by machine learning algorithms. And the way to do it is by a convolutional neural network, which has a downsampling branch. This is given here up to the latent space. And then we have an upsampling, which is coming here. And I have put the input picture here, which goes basically here, enters here. And I have indicated how this picture changes if you go from level to level here. And level to level means you are applying operations which are convolutions and so-called max pooling operations, in which this is a way how you basically reduce the information in several ways, and at the same time you extend the feature space by generating several samples of these data, as you can see here. So we have 128, but then we have 32 of these slices, and so on and so on. So eventually, when you pass through such an algorithm, what you get is this. And this is a classification because you have basically segmented your image into high transport regions of enhanced local convective heat flux and the rest. Yeah. And this can be used to understand now the transport. These are the regions where most of the convective heat flux is going through. And you see this goes through several topological changes. There are defect generations and defect annihilations. And this is a way how we can monitor the transport and the dynamics of the transport in an extended convection flow. We reduce it basically to a temporal planar network. And then from there, one could continue to build models on the basis of these reduction methods. Let me come to the second topic, which is now we want to learn the dynamics in some sense. And we want to generate a model that reproduces the low order statistics. So the idea is, again, we take the data, we somehow reduce the data, we feed it into our neural network, we run a dynamics with this network, and in this way we have an equation-free and data-driven reduced order model for the dynamics of the large-scale structures in our system, which we, as I said before, term the turbulent superstructures. We have done this with two examples, a 2D Rayleigh-Bénard convection flow and a 2D moist Rayleigh-Bénard convection flow. The latter one is more challenging because the model is more comprehensive, and you really can test the model with respect to derived quantities such as the cloud cover or the liquid water flux. That is a little bit more challenging. So that was the motivation to go one step forward in terms of the complexity. Can a recurrent neural network reproduce the low order statistics and the large scale flows? That's the question. Here's the model. We basically obtain from a POD decomposition of our turbulent fields the time-dependent POD expansion coefficients. This is the AT in our case. The spatial information about the structures is encoded in the POD modes. So that in that respect, we have already reduced the model to some degree. And now we are feeding a few hundred of these exponents into our neural network. So we have the data reduction step is done. Now it's coming with now is the machine learning modeling aspect. We take these data as an input layer and we map it into a reservoir. A reservoir is a big random network. It's you can think of it as a very, very simple model for the human brain in some sense. And this reservoir is basically generated as a big random matrix, which is characterized by a certain spectral radius, rho of A. And in this reservoir, we are running a dynamics, which is given here by this equation. And there are several ways to do that, but I have taken here a way that looks like a simple ODE system or a nonlinear ODE system. So the reservoir state at time t plus t1 is prefactor times the old state plus 1 minus the prefactor times a nonlinear activation. The tangent hyperbolicus is a typical model for a nonlinear activation function. It's like a neuron gets fired in our brain, or some neurons get fired in our brain. And inside we have the input information and we have the reservoir dynamics. So the big advantage of this particular architecture of recurrent neural networks, that means neural networks with a short-term memory, is that we have to train it only with respect to the output layer. The output layer is basically when we are mapping the reservoir back to our original variables, which are the POD expansion coefficients. And this is, so this one is trained, and the training output layer is a standard procedure which is by far less comprehensive than the typical training procedures which you have in deep neural networks, which require a forward and backward propagation of the information through the network. So once this is optimized, we get the model in the prediction phase. And there are several hyperparameters which have to be tuned. It's the leakage rate alpha, it's the spectral radius, it's the number of nodes. And typically this number is very big. It's by a factor of 10 or even more bigger than the original number of degrees of freedom. So there's a little price to pay, but it's very sparse. So the node density is typically 20%, which are really active. So in this way, we are now in the prediction phase. And yeah, we don't use all Fourier expansion coefficients. We typically truncate, and this is shown in these figures. Here we take, for instance, the first 100, 150 exponents, and we have already 83% of the total variance, which is covered by these things. So you have to truncate your POD model, certainly. And then it is trained, and then this is the prediction phase, and the system is fully turbulent and highly chaotic, so you cannot expect that the trajectories remain together very long. And but the statistical behavior, which we see, and red is the model, and green is the real data to compare with, the test data, is it seems to give the same statistical behavior, these time series. And that can be quantified a little bit further. First, we can derive certain measures that quantify the errors, but we can also take our physical quantities such as PDFs, such as convective heat flux profiles, such as temperature fluctuations, such as liquid water flux in the moist convection model, or the cloud cover in the moist convection model. And the agreement is very reasonable. It's surprisingly well going here for all the cases. There's a gap between the red and the blue and green curves, and that is the truncation of the POD model. As you can imagine, we are losing some of the variance already here because we have taken only 83%. If you want to close this gap further, you have to include more modes to get the threshold higher. What's next? Well, the POD analysis in its own is already quite expensive, and you can imagine if we would go to 3D flows, it gets even more expensive. So the idea is to take something which works probably a little bit easier. And one way is to use autoencoders, decoders. It's basically a structure which I have talked about in the first part of this machine learning chapter, and combine it with our reservoir computing model. That's what we are trying currently, and the first results look promising in that respect. The next thing is, a problem with all these models is always that they are trained for a specific data record, and then the generalizability of this model is rather limited. And that can be, at least in parts, compensated by so-called transfer learning. And that is something which we are looking at the moment. And the third thing is, it probably is also good to bring a few more physical ideas into the design of these networks. In particular, the multi-scale character of turbulence is not reflected at all in this model, and that is something which we are now trying to solve. Summary of part 2. Deep convolutional neural networks reduce 3D turbulent superstructures to a slowly evolving planar transport network. And reservoir computing models are able to predict the low order statistics in two-dimensional dry and moist convection. The corresponding references are given here, and the moist convection stuff is under review currently, and you can download the paper from the archive. So now we're doing the next step. So why quantum computing? Well, you probably know that this is really a rapidly emerging field of research, and also in view of machine learning applications, people start to develop and think about how we can run machine learning algorithms on quantum computers. The current stage of quantum computing should be compared with what we had in terms of the semiconductor technology in the late 40s, early 50s. And I have pulled out from the net this picture, which is a replica of the first transistor, which was developed in 1947 in the Bell Labs. And I mean, we went basically from 1947 and such a structure to things like this. This is the SuperMUC in Munich on the Supercomputing Center. So, but everything which we have in terms of quantum computing is more or less comparable to what we had in terms of semiconductor technology some 60 years ago or even 70 years ago. So this is really a very early stage, even though this facility looks already quite impressive in terms of the technology that goes into these quantum computing systems. We are in the era of the so-called NISQ devices, noisy intermediate scale quantum computing devices, and they all have something like less than 100 qubits. So why quantum computing? Well, there are a few points which make quantum computing very interesting. And I would like to go with you quickly through this diagram, which compares the classical bits as we use them on our cell phones or in our laptops with the quantum bits. So the classical bits can be either 0 or 1, while a qubit is basically a superposition of these two states. So there are infinitely many states which would fill a unit sphere which represents all possible qubit states. Alpha and beta are complex numbers, so the qubit is basically spent in a C2 space, in a two-dimensional complex space. And now you go to n bits, you go to registers. You can do it in a classical way, and in the quantum way, it is basically a tensorial product of these individual qubits. That means the dimension of the space which is spanned by a quantum register consisting of n qubits grows exponentially fast with the power of 2 to n. So that's something which is very important and which makes it very interesting. So we have the classical operations, which we all know on a classical computer. They can be irreversible, like the NAND circuit, and memory can be erased. This is partly restricted or limited on quantum computers because they follow the laws of quantum mechanics. That means everything is linear and reversible because the time evolution is prescribed by unitary transformations. And one consequence is that qubits cannot be reset just in the middle, at least not with present quantum computers. They have to be uncomputed. So there are 2 points which make quantum computing interesting. The one is exactly this exponentially growing dimension of the data space. So that means it's possible to model high dimensional phase spaces as we know them from fluid dynamics. And the second thing is something which is new and only possible in quantum mechanics. That's the entanglement between qubits, which basically means that you can have a kind of far distant interaction between these qubits. And quantum systems, loosely speaking, and that allows for a very efficient encoding of strong correlations and nonlinearities. Yeah. So the quantum computer typically is is made of 3 units. It's the input unit, it's the processing unit, and it's the output unit. And you have to load classical data onto your register, onto your 2n dimensional state, which is here. Then it evolves with respect to unitary transformations. And then the information is read out by a measurement. And as you know, when we do a measurement in a quantum system, everything collapses onto that state, and then it's over with the quantum computation. You have to start anew. So our idea, or our current intention, is to extend the classical reservoir computing model, which I just presented to you some minutes ago, to a quantum reservoir computing model. So what was the reservoir state at a time t is becoming now a density matrix at a time t. What was the nonlinear activation by a tangent hyperbolicus in our classical model will now be a so-called swap operation, where we basically exchange several qubits. The reservoir size is given now by 2 to n, the number of qubits. The leakage rate remains, and the dynamics is given here. I don't want to go too much into the details, but what you have to do is you have to glue together unitary transformations. You have to generate entanglements between the different qubits, and then it becomes an extremely complex reservoir state that does the same job as our very complicated random network in the former. And we have done a first test of our algorithm, and that is close to what has been reported here in these works, which I have referenced here. And it's a so-called NAMA benchmark test. That's a nonlinear time series, which you can generate by a very simple model, which you see here. You have an input, which is following this periodic function here, and that couples nonlinearly into this recursive formula, and it generates some kind of fluctuating time series. And that's exactly what we would like to learn by the quantum algorithm. And here are the very first results of that. It's the classical reservoir computing model, which is shown at the top. And I have again listed the hyperparameters here, and the corresponding quantum reservoir computing model, which we have designed out of 8 qubits, and in a so-called quantum simulator. That is also doing a very good job. As you can see here at the bottom, it's the same time scale here. It's about the same amplitude. So it looks really that this very little simple model does a very good job. Okay, that's all. I'm coming to the end of the third part, in which I have just shown you some very, very first results about the extension of reservoir computing model to a so-called quantum reservoir computing model. And we have just finished in the past days the first successful tests and verifications of that. The next step would be to go to simple dynamical systems and to try to model a simple nonlinear dynamical system on a quantum computer. And there's another effort going on in parallel to that, where we are basically trying to set up a scheme of rules how to translate a nonlinear dynamical system into a quantum computational one. And with this summary, I would like to thank you for your attention, and I'm ready for questions. Thank you.